the last session on fundamentals of communication theory, classical communication.
Just a second. I think we have some audio problem here.
Oh,
Yeah, now it's fine.
okay. Is my voice coming across well?
Yes, yes, yes.
Okay. So today the focus will be on the several digital modulation techniques.
So we can begin. We can take a 5 minutes break around 3 minutes. Sorry, around 3 p.m.
Sure. Okay, so I'll begin my presentation. Let me just share my slides. Okay, so uh, we will be studying the conceptual aspects of digital communication, digital modulation techniques by starting with a very basic modulation scheme, which is called binary phase shift keying. And here we will be using a simplified model. Okay, so what do I mean by simplification? Is that this model is going to abstract out an inherent part of the modulation and demodulation or the modem functionality of any digital communication scheme, which is frequency up conversion at the transmitter and frequency down conversion at the receiver. We briefly touched upon it yesterday, and we said that uh, in an ideal sense, these two are completely inverse operations of each other, right? They are complementary operations. Frequency up conversion translates the spectrum of the informative signal uh, to the desired radio frequency, and that upconverted signal gets transmitted from the antenna, because the analogy that we gave yesterday is that once you upconvert the signal to high frequency, its transmission like becomes equivalent to or nearly frictionless motion on a surface of some object. And so that is the reason why we are upconverting to some high frequency, typically a radio frequency. And at the receiver, we cannot actually comprehend such high frequency uh, energies. Our brains are not wired to make sense of it. And so that received signal, which is at a high frequency, is down converted to back to the center frequency of 0 Hz, what is also known as baseband, by the process of down conversion. And that frequency up conversion and frequency down conversion, in some sense, cancel each other out, ideally. In reality, they may not. And therefore, there is a lot of design involved in how to address imperfect cancellation of what is implemented with transmitter in terms of frequency and conversion. But that complication need not bother us as of now. We also mentioned briefly that with this, apart from kind of a Fourier transformation type of perspective, there is a linear algebraic perspective that we can bring to bear to understand this operations of up conversion and down conversion. Frequency up conversion process, we can think of it as a synthesis operation. Frequency down conversion, we can think of it as an analysis operation. Synthesis and analysis, again, are inverses. They can be thought of as being implemented using matrices which define complete orthonormal bases. Basically, orthonormal matrix has its transpose as its own inverse. And so what is implemented at the transmitter in terms of frequency up conversion using an orthonormal matrix can be reversed at the receiver simply by multiplying with the transpose of that matrix. And so that kind of allows you to recover back your original informative symbols. Okay. Now, we saw that a general model of communication, in a general model of communication, we may have several representations, but the one which is common is to think of the actual information bearing signal, which is at baseband, not yet upconverted to RF frequency, as comprising a complex number with in-phase and quadrature, real or imaginary component, SI and SQ. This is an example of a second order modulation scheme. And many of our today's communication systems actually operate on this second order schemes. But it does not have to be second order, it can be higher order as well. Anyways, so this is what I was mentioning very briefly, that the process of frequency up conversion can be thought of as taking an information bearing vector S of m, which for the second order scheme is only a two-dimensional vector. The first element SM1 would be SI, second element SM2 would be SQ, and passing it through some orthonormal matrix G mode. And that output of that matrix vector multiplier is actually equivalent to a radio frequency signal at some carrier frequency f of c hertz. At the receiver, in the absence of noise, we receive G mode times Sn. The down conversion can be mathematically shown to be equivalent to multiplying G mode transpose to R. So when you do that, what you get is G mode transpose times G mode times S of m. And because this matrix G mode is orthonormal, G mode transpose G mode becomes identity matrix, and you recover back the originally transmitted signal at the baseband, which is the actual information bearing signal. Okay, so that essentially is the principle of frequency up conversion and frequency down conversion viewed from a linear algebraic perspective. Now, here, as I have shown, this vector S of m is two-dimensional. It does not have to be two-dimensional. It could be up as many as k dimension, capital K. In capital K, you can choose it to be as large or as small as you wish, but the principle remains the same. And other thing that we will see is that once we apply this linear algebraic representation, even this additive noise can be represented as this k-dimensional vector n. And this is the process of multiplying the received signal with G mode transpose that I just mentioned. It is implemented in signal processing using some mixer followed by an integrator and dump, also sometimes known as a match filter. And the receiver implements a kind of a bank of capital K such match filters, one for each of these basis functions, G1 up to G of K. And then the output of the basis functions gives us some scalar values. And so all of this transmission uh, channel propagation, and at the receiver, the match filtering operation, because of this property that this matrix G mode has, meaning that it is its transpose is its inverse, all of the part which is shown in the red kind of uh, cancels cancels out, and what we get is simply a very simple diagram that the transmitter vector, transmitted modulated symbol is a k-dimensional vector. There's total of k component. These components go through an additive noise channel which introduces this vector and which is also k-dimensional. And then the receiver gets a k-dimensional vector R1 to R capital K. Now, in the context of this diagram is what we are now talking about, specifically for the case where this capital K is just 1, not even 2. Because capital K is 1, there is only one scalar that is transmitted in this BPSK scheme. The noise is now also a scalar, just a single dimensional value. And then the received signal is also a scalar. Now, the question is that in the presence of noise, how does the receiver, let's say some optimal detection method, how would it decide whether bit 1 was transmitted or bit 0 was transmitted whenever it receives a particular value of R? Okay, so that is going to be the question that we will talk about. Okay, so let us look at it. This is some probability math. It says that if x equal to 0 is transmitted, then according to the BPSK scheme, as we showed here, whenever x is equal to 0 is transmitted, it gets mapped into minus a volt. And that minus a becomes a constant addition to a Gaussian noise signal n, which is 0 mean and variance of sigma n squared. So therefore, given that x equal to 0 is transmitted, the conditional distribution of R is given by this formula. This is the formula of Gaussian distribution, whose mean is minus a, and the standard deviation is sigma n. Okay, so I assume that you are familiar with Gaussian distribution, and this is simply saying that when x is equal to 0 transmitted, the received signal is Gaussian distributed. Why Gaussian distributed? Because we are modeling the noise to have Gaussian PDF. The mean or the expected value of that Gaussian distribution is minus a. Why minus a? because whenever the transmitter wants to send bit 0, the BPSK scheme converts 0 into minus a volt. So that is why this PDF is realized. Same way, if we want to determine the conditional PDF of R given x equal to 1, then it follows similar formulation, except the mean now changes from minus a to plus a. In this equation where my mouse is, the first equation, the mean is minus a. Here the mean has become plus a. That is the only thing that has changed, because all the other aspects of the noise don't change. Now there is a Bayesian method of detecting BPSK symbols, which evaluates the same ratio lambda that we have talked about earlier in the context of coronavirus disease detection, if you recall, where we evaluate the ratio of likelihoods, the probability of R given x equal to 1 divided by probability of R given x equal to 0. This is called maximum likelihood reception. And this applies only when x equal to 0 and x equal to 1 occur with equal probability, meaning that q is equal to 0.5. Remember, x is the Bernoulli variable. Bernoulli variables are characterized by the value of q, which is the probability that x is equal to 1. So when q is equal to 0.5, there is equal chance of zeros and ones. Then the optimal Bayesian method becomes this maximum likelihood technique, which is simply asking which of this conditional distribution is greater. Whichever is greater, I will say that the corresponding value of x is transmitted. One way to say which one is greater is to take the ratio, and whenever the ratio becomes 1 or greater than 1, then we say x equal to 1 is transmitted. Otherwise, we say that x equal to 0 transmitted. Okay, so that is the main idea. I have plotted these two PDFs. This one in red is the PDF of R given x equal to 0, PDF of R given x equal to 1. In this plot, I have taken A is equal to 1. So when the transmitter sends bit 1, the PDF is centered at R equal to 1. The mean value becomes plus 1. When transmitter sends bit 0, the mean becomes minus 1. So looking at the picture now, suppose at the receiver I get a value of R which is given in this green circle that I have put on the x-axis, close to 0.5. What would maximum likelihood detector detect in that case? Given this value of R, what would the BPSK detector that implements this ML rule say? Yeah, the answer is that the ML rule will say that x is equal to 1. Why? Because which of these two PDFs are stronger at 0.5? Obviously, the blue one. The blue one corresponds to x equal to 1. Now, as I suppose I slide this green circle toward the left. So initially, as I slide the green circle, the ML detector will still keep on saying that x is equal to 1. At what point will the receiver say that x is equal to 0 now? Right. So when R becomes 0, at the point at which these two PDFs are equal, that ratio becomes equal. On the left-hand side of that line, that point, meaning that whenever R is negative valued, the detector will say that X is equal to 0 is more likely. Otherwise, it will say that X is equal to 1 is more likely. Effectively, the detector is putting a boundary at R equal to 0. All the positive values of R are detected as X equal to 1. All the negative values of R are detected as X equal to 0. Now that I have formalized it in using some standard mathematics here. I took that likelihood ratio, which is given like this. In the third line, I removed the common terms. So I get the ratio of exponents. Now, even inside the exponents, there are common terms like r squared, a squared, etc. Once I get rid of them, and then I combine the terms in the numerator and denominator, I get the fourth line. And then the last line is the simplification of the fourth line. So the likelihood ratio for the BPSK reception in the case of Gaussian noise is simply exponent of 2RA divided by sigma n squared. Now, what mathematicians said is that this is still not very clear enough. Uh, by the way, I'm plotting that likelihood ratio here. And you can see that when R is greater than 0, likelihood ratio becomes positive in favor of X equal to 1. And so we say X is equal to 1 is transmitted. When R is negative, the red colored line becomes stronger than the blue colored line. And so we say X equal to 0 is transmitted. Now, coming back to that math, if our interest is to evaluate when is lambda greater than or equal to 1, then we can kind of play a trick. Instead of looking at lambda, we can do logarithm base e of lambda. And that is because comparing lambda equal to 1 is same as comparing log base e of lambda to 0. The reason why mathematicians took logarithm of lambda is because logarithm and exponent are inverse functions, they cancel out. And so I have to just compare 2RA divided by sigma n squared against 0. Which is to say that I just compare R against 0 because A and sigma n squared are constants. They don't influence this comparison. They are positive constants, so they don't influence this comparison. So comparing 2RA divided by sigma n squared against 0 is same as comparing R against 0. And so the receiver rule can be written that whenever R is greater than or equal to 0, we say that bit 1 was transmitted. When R is less than 0, we say bit 0 was transmitted. R equal to 0 is the decision boundary. I saw a question that at R equal to 0, why don't you say X hat is 0? Why do you say 1? Yeah, you can say that. It's fine. The thing is that it probably doesn't matter because the chances that R will be exactly 0 is minuscule. So it doesn't matter what you say at that point. Both are fine. Or whenever, in case you happen to have a case where R is exactly 0, you toss a coin and the coin doesn't land on a face, but it lands on the edge. That happens, you can say either it's heads or tails. It doesn't matter. So if R is equal to 0, you can randomly say X hat is 1 or X hat is 0 because both are equally likely at that point. Now, what happens is that such a rule is actually same as minimum distance detection rule, right? If you don't do all of this elaborate math and you go back to this um, chart that I have shown, you even forget about the y-axis entirely. You just look at what is happening on the x-axis, right? We just moment ago we said that as I slide this green circle toward the left, exactly at r equal to 0, we flip from deciding x equal to 1 to x equal to 0. The reason that is happening is because r equal to 0 is exactly halfway between the two transmitted symbols, +1 and -1. At r equal to 0, the distances are same from these two constellation points, two symbol points, +1 and -1. On the left-hand side of that point, the distance to the red one, -1, becomes smaller, and so we decide -1 was transmitted. On the right of that boundary, the distance to the blue, +1, becomes smaller, and so we decide +1 was transmitted. So actually, we can say that we are just, whenever we get some value of r, we measure its distance to the two possible transmitted symbols, and we decide that symbol for which the distance of r is the smallest. So that does not require us to use any of this Bayesian rule. All we do is just calculate the distances and minimize them, and they give exactly the same answer as the optimal maximum likelihood technique. It turns out that the equivalence of minimum distance detection and the optimal maximum likelihood detection holds, provided one requirement is that the channel has to be Gaussian noise. It has to be introducing Gaussian noise. If the channel is introducing some Laplacian noise, or of some other impulse noise or short noise, then uh, the minimum distance detection and the maximum likelihood detection, uh, they are not equivalent. And the second requirement here is that we assume that x equal to 1 and x equal to 0 are equally likely. If they are not equally likely, then we cannot use maximum likelihood rule. We have to use maximum a posteriori rule. What is maximum a posteriori rule? Instead of taking ratio of the likelihood functions, r given x equal to 1 divided by r given x equal to 0, maximum a posteriori maximizes probability of x equal to 1 given r, basically posterior on x. When the priors are the same, the maximizing the posterior on x becomes same as maximizing the likelihood ratio, which is this ML rule. When priors are not the same, then we still have to calculate this ML ratio lambda, but then we have to multiply by the ratio of the priors. And that then becomes map technique. The answer given by the map technique is not going to be the same as the answer given by this minimum distance detection rule. Okay, so what I'm trying to say is that minimum distance detection rule is a very powerful technique. It is applied in a lot of different settings. It is very simple to understand. We all are very familiar with calculating distances. In this case, we are calculating just the squared Euclidean distance. And that is all there is to it. Especially in the multidimensional case, appreciation of minimum distance detection becomes very natural. But then one thing that we have to keep in mind is that the optimality of maximum minimum Euclidean distance detection rule is not guaranteed. Whereas if you go with maximum likelihood or map schemes, then you know that you are always tied to the optimal derivation technique. Okay, I'll quickly go over the uh, probability of bit error, and we will again do some probability math. Uh, we want to know that this maximum likelihood detector, with what probability it gives the wrong answer. Okay. So to evaluate that probability, given that our decision boundary is at r equal to 0, assuming that x equal to 0, x equal to 1 are equally likely, the probability of error, how would you calculate it? So maybe there is this detailed derivation that probability that error is equal to 1 is that the receiver made an error when x equal to 1 was transmitted, plus the receiver made an error when x equal to 0 was transmitted. So it's summation of these two joint probabilities. Now, what is the first probability? Joint probability x equal to 1, error equal to 1 is just the product of the prior on x, probability of x equal to 1, times the conditional e equal to 1 given x equal to 1. And similarly, the joint probability x equal to 0 equal to 1 is the prior on x for x equal to 0 times the conditional e equal to 1 given x equal to 0. All that this says is that what is the probability that the receiver makes an error when the transmitter has sent x equal to 1? That is this probability. What is the probability that the receiver makes an error when the transmitter sends x equal to 0? That is the second conditional. So now you have two error probabilities. Your overall error probability is going to be an average of the two. How do you calculate the average? Well, you just multiply by the corresponding p-values, that is the priors. Right? This is the standard technique, it's a standard formula for calculating expectation. Okay, now we have already said that x equal to 1 and x equal to 0, they both have a probability of 0.5. So that those terms are easy. We'll just take them as 0.5. How do I calculate probability of error being equal to 1 when x is equal to 1 is transmitted? So for that, I have to think, okay, when the transmitter sends bit 1, when will the receiver make an error? Because the decision boundary is r equal to 0, and we have said that all the positive values of r are going to be detected as x equal to 1. What does it mean? The error will be made only when r is negative. Correct? Yeah. As Himani Kaushal correctly said. What about the second case? What is going to be the situation when the receiver makes an error when x is equal to 0 is transmitted? Well, again, that happens only for the cases when r is positive. Yeah, r is positive. E equal to 1 doesn't mean that error is 100%. All it means is that the transmitter sent a particular bit as a BPSK symbol and the receiver got confused. Okay, that is all that it means. The probability is what we are trying to evaluate. And if the receiver is confused all the time, if P values are 1, then you can say that probability of error is 100%. But right now, we are just evaluating what that is. So this is the third line that comes straight away from the second line. And now we are going to evaluate these two probabilities. probability of r equal to r less than 0 when x is equal to 1, r greater than 0 when the x equal to 0 is transmitted. Okay, now you see that this first conditional probability of r less than 0 when x equal to 1, we have already kind of visually seen, right? What is this? This was the blue colored PDF in our chart. Probability of r given x is equal to 1. That is the blue colored chart. What is the probability that r is less than 0 when x is equal to 1? If I take the part of this blue colored PDF, the blue colored shape, if I take the area under the blue color for r less than 0, so if you can see my cursor, Professor Mithrwal, are you able to see my cursor? Okay. So you see the area where I'm moving the cursor? If I take the total area, that becomes the probability that r is less than 0 when x is equal to 1 is transmitted. What will be the probability that r is greater than 0 when x is equal to 0 is transmitted? Well, that is going to be the mirror image of that area under the red curve. In fact, if you just wait for a moment, I have actually shown these two areas graphically. So one thing we see right away is that there is a symmetry to it. Both these areas are going to be identical. Okay. So I just need to evaluate one of the two areas, and then the second area is going to be the same. I'll just evaluate the area for the case when x is equals to 0 transmitted. I'll evaluate the area under the red curve now over the positive values of r. So then this becomes the integral that I need to evaluate, given that I have the Gaussian PDF. And this integral is actually not solvable in closed form, but there are some numerical methods that have been implemented, and the numerical values of this integral for different values of a and sigma n have been evaluated, and they are tabulated in the form of a Q function. This Q function is a very well-known function in probability and statistics. It is also related to the error function or the complementary error function. And in today's tools like Python and MATLAB, these are inbuilt functions. Okay. So Professor Mithrwal?
Yes.
Yeah, okay. Maybe can you mute yourself because there is some echo coming. Okay, thank you. So the answer is that the error probability is given by Q function of A divided by sigma n, which is the answer to this integral. Isn't it possible to increase the cursor size to make it more visible? I don't know. Maybe there is. Let me see. Maybe I can try laser pointer. Yeah. Maybe this helps.
Yes, this is fine.
Yeah. Okay. So basically the point of this math is that the probability of demodulated bit error is given as Q function of A divided by sigma L. And I have given here some detailed derivation of how I got this Q of A divided by sigma N. I won't go over it. We'll just accept that it is Q of A divided by sigma N. So basically, what we have done is for BPSK, we have kind of understood what the constellation scheme is. Constellation scheme is shown typically by this type of diagram where the transmitted symbols are shown. For BPSK, they are 1 and -1. The energy of the transmitted symbol is the squared radius of this symbol points, or what are known as constellation points. So for BPSK, the energy per symbol is taken as being proportionate to A squared, because individually these symbols are at +A and -A. And then at the receiver, we have seen that because of the additive noise, the received symbols don't remain exactly at +A and -A, but they form sort of a noisy kind of blurred images of +A and -A. So I have shown here what could be the received symbols if the transmitter sent, let's say, 100 symbols, out of which roughly about half were +1, half were -1. Because of the noise, the symbols which were received when the transmitter sent +1, they were not exactly at +1, but they were a little bit shaky version of +1. Same way for the -1. So there are about 50 red dots around -1, around 50 red dots around +1. And you can actually look at the spread of all of these red dots, and from that you can get an estimate of what is the variance of the noise introduced by the channel. This is a very standard technique. It is called error vector magnitude. Well, here the sigma, I don't know what you mean by sigma. Sigma is the standard deviation. We are not displaying sigma here. But if you are meaning to say that the spread doesn't look uniform, it is because I did not simulate enough number of points. This may have only total of 100 points. And so with 100 points, you may not get perfect symmetry. But if I had simulated maybe 10,000 points, then you would see that the spread of red around each of the two blue dots would look about the same. Okay, so that is the idea. We also saw that the optimal Bayesian technique, maximum likelihood technique especially, how to formulate it. And we understood that because maximum likelihood is similar to minimum distance detection, for what we did for BPSK, we can extend it to even on-off keying. So that is what we did. Now, the minimum distance detection, what it says is that whenever I get a received noisy signal, which is one of these blue dots, the red is what I have transmitted. Then I calculate two error vectors, E1 and E2, from the two symbols. And I select that symbol whose length is smallest, in this case, E1. So that leads me to say that the decision boundary for BPSK should be at R equal to 0. Now remember, yesterday we talked about on-off keying, which is very similar to BPSK. Bit 1 is transmitted using +A, But bit 0, the transmitter is switched off, so it would be equivalent to a point right at r equal to 0. If I draw the diagram for on-off keying, it will have this point unchanged at plus a, but the point corresponding to bit 0 would be at r, at this point, at the origin. What will be the decision boundary for on-off keying? Right, it will be again halfway between the two transmitted symbols. Why halfway? Because the halfway point is the transition point at which you flip your decision regarding which point is closest. Okay. It allows us to also perform theoretical evaluation of the probability of bit error. What we did was we calculated what is known as the tail probability of Gaussian PDF, and the answer becomes in the form of a Q function parameterized by the ratio A divided by sigma n. And I meant to give you some assignment, which I did not at the end of yesterday's lecture, where you would have simulated this BPSK transmission scheme in the Gaussian noise. And if you did that simulation, you would have measured this probability of bit error curve. And if you compare it with the theoretical expression, which is Q of A divided by sigma n, then you would have seen that it matches exactly the simulated profile. Now, in the absence of doing this lab, you don't get that kind of full confidence about how the BPSK detection that you talked about, the maximum likelihood detection, how to implement it, how it works, etc. But still, we can get some insights purely by looking at this expression of theoretical error probability. And we observe that it depends on the ratio A divided by sigma n. So the absolute value of A, which is that, remember, square root of the transmitted signal power or signal energy, the sigma n, which is the square root of the noise power, their absolute values don't matter. What matters is the ratio. And this ratio is expressed basically as square root of SNR. Okay, so that is what it amounts to, that the performance is determined by the SNR, signal to noise ratio. The other thing is that, assuming that the symbols are equally likely to be transmitted, both the symbols corresponding to bit 1 and bit 0 are equally likely to be transmitted, and the channel is Gaussian, then irrespective of what transmission scheme that you choose, the decision boundary is always going to be halfway between the constellation points. Okay. Now, there is a hard way to understand why this is the case, where you evaluate the conditional PDFs, you apply the maximum likelihood method, and then solve the formula. The easy way is to say that under these assumptions which I outlined, the maximum likelihood is equivalent to minimum distance detection. And for minimum distance detection, the decision boundary better be the halfway point. Because if it is not, then you are not doing minimum distance detection. So let us consider these three different schemes. The blue dot corresponds to the symbol when x equal to 0 is 1 is transmitted. The yellow is when x equal to 0 is transmitted. Now, in this case, the error probability also depends only on the distance between the blue and the yellow, okay? Not their exact amplitude. This requires slightly deeper understanding of the derivation that we just now did. Basically, the error probability is the area under either the green or the blue curves. They both are identical areas, so their values are the same. And what happens is, if you imagine these two PDFs, the bell-shaped PDFs, you imagine that I bring S0 and S1 closer to each other. Okay? So I bring them closer to each other. Then you can imagine that this tail probability, the area corresponding to green or blue, will increase. If I bring them farther apart, then the tail probabilities will reduce. So what matters is the distance between S0 and S1. It wouldn't matter if I take both S0 and S1, keep the distance between them the same, but add, let's say, constant of 5 volts or 39 volts or something. It wouldn't matter in terms of the area under the blue and the green, because in terms of the shape, I am not doing anything. So that is the reason why we say that the error probability depends only on the distance between the constellation points. And so that error expression that we had, Q function of A divided by sigma n, well, A is D divided by 2, right? What is the distance between two QPSK symbols at plus A and minus A? Distance is obviously 2A. Because one is at plus A, another is at minus A. The distance between them becomes 2A. And therefore, A becomes D divided by 2, distance divided by 2. So A divided by sigma n is same as D divided by 2 times sigma n. And so that is the another expression for the error probability. So let's see. You can evaluate the error probability for scheme 1, scheme 2, and scheme 3 because their expressions will be given as shown here. D divided by 2 sigma n. Okay. Now, before we go to the next topic, I think we will take some 5-minute break pretty soon. But I want to mention one last thing, which is that because the distance depends on, the error probability depends only on the distance, you can say that scheme 3 and scheme 2 will achieve the same error performance, which is Q of 1 divided by sigma n. Scheme 2 and scheme 3 are identical in terms of the error performance. But what is the average symbol power for scheme 3? Remember the way we have defined energy or power of a symbol is the squared radius from the origin, a squared distance from the origin. So these two symbols both are at the energy of +1. Because they happen equiprobably, the average energy becomes +1. In contrast, what is the average energy for scheme 2? What is the energy of this symbol where my cursor is? Any thought? Yeah, I think the answer is correct. Hemani gave the right answer. 6 square plus 4 square, 36 plus 16 divided by 2 because we have to do average. So that becomes 26 units. So scheme 2 expands 26 times more energy on average per symbol compared to scheme 3. But it gets the same performance. What this tells us is that scheme 2 is a bad idea. We shouldn't be doing scheme 2. It is wasteful of the energy that it emits. And communication engineers have thought about it, and they have given us the statement of their observation, which is also evident from this example. What they say that statement says is that the decision boundary, this red colored line, we should never center it at any place other than 0. Because if we do so, the energy that we are sending to represent that decision boundary is wasted energy. Actually, we never transmit decision boundaries. So in a way, we are never consuming energy to send the end to decision boundary. But the point is that the halfway point between the two transmitted symbols, if it is away from 0, then you are wasteful of energy. And so if you look at scheme 1, its error performance is better than scheme 3. But it is also not optimal because this decision boundary is at -0.5. So you could actually come up with a better version of scheme 1 where both the yellow and the blue are shifted toward the right by 0.5. So instead of -3 and +2, you did -2.5 and +2.5. Then you will get a better version of scheme 1. It will be more efficient in terms of energy. But as soon as you do that, -2.5 and +2.5, it becomes same as BPSK with A equal to +2.5. So in some sense, BPSK is optimal. It achieves the best error probability given a particular energy constraint. Okay, with that, we'll take a short 5-minute break and then we'll meet at 5 minutes after 3. Thank you.